the previous video, I pointed out some of the issues with our insert range. I had a bug there, and then we also had an optimization issue where we were enumerating through all the items several times by calling count. We centralized that, so we only call count once. We need to call count because IEnumerable does not provide a count nor a length property, so we have to brute force it, call count, store that value, and then reuse it several times. But that is not the biggest issue with our implementation of insert range. I noticed something even greater, something that would be more expensive. And hopefully you caught that. Let me see if I can illustrate it here. Here are our underlying number of items. I've reduced it down to 4 just to keep this video simple. I'm going to draw our underlying array. The capacity is 4 because we set the initial capacity to 4. And also our count is 4 because that's the number of items that I'm sticking inside of the list. And again, this optimization I'm showing you is only for one scenario, but this scenario could come up, and it could come up quite often if you're not careful. Now I'm trying to insert 3 more items, and I'm trying to insert them at index 2. Okay, this is index 0, index 1, index 2, index 3. I want these items to start to go to right there. Well, let's look through insert range. Let's just trace through this and see exactly what's going to happen as we run this insert range. The first thing we're going to do is count the number of items inside of here. So that's 1, 2, 3. That's kind of clunky, but we have to call count at least once, and we know that there's 3 items. We ensure capacity, and inside of our ensure capacity code, we're either going to double the length of the underlying array, or we'll go bigger if we require a bigger amount. We saw that in previous videos. In this scenario, doubling the length of the array will give us 1, 2, 3, 4. 4 times 2 is 8, so we'll get 8, and 8 is greater than 1, 2, 3, 4, 5, 6, 7 items, so we'll end up doubling the size, the capacity of the array. So let's draw our new array up here, and that is doubled. Sorry, that's on the edge of your screen, but we are doubling the length or our capacity. So there we go. There are our original 4, and then I'll make 4 more right here. So 1, 2, 3, 4, 5, 6, 7, 8. We've created the new array. The next thing ensure capacity will do is copy all the elements we already have into this new array. So 32, 83, 99, 42. And now this new array is our underlying array. The other array we abandoned. It's open for garbage collection. There we go. We're done. That is our ensure capacity call right here. Then we come in and say, hey, we got to shuffle everybody down. Looks like they're trying to insert at index 2. So 0, 1, 2, 3, 4, 5, 6, 7. They're trying to insert at index 2. There's 3 guys here, so everybody has to move down 3. So the 42 will go 1, 2, 3. We'll copy the 42 to right there. And then the 99 has to come down here. We'll copy the 99 here. And then we will copy the new guys in. 55, 65, 75. Let me get my eraser here. And we'll put 55 right there. We'll overwrite the old 99. And the 65 will overwrite the 42. 65. And then these blanks actually have zeros in there because that's the default value for integer type in this case. And so the 75 will overwrite. That looks like a 25, doesn't it? That's a 75, and we'll overwrite the 0 that was right there. And there we go. We have inserted our range. Did you notice kind of an extra step there while I was drawing in here? Did you notice some extra moves that we might be able to eliminate? If you still can't see it, pause the video. Think about it. See if you can figure it out before I tell you. The issue that I noticed is we had this array down here. We had that original array down here. It stored all these items: 32, 83, 99, 42. You can tell I'm going fast because the handwriting's sloppy. We copied all the items into a new array, and then we copied again. Okay, we copied. To do the shuffle, we had to copy the 99 and the 42. Not only did we copy them to the new array, but then we recopied them. We reshuffled them. You know, why don't we just get smart and say, you know, if we're going to copy them, let's copy them once. If this underlying sequence down here is really long and we're trying to insert towards the beginning, that's going to be super expensive. We don't want to double copy. That's expensive. Why don't we just take this 99 and instead of copy, let's just copy. Right? Let's put the 99 exactly where the 99 should have, needs to end up when we do any sort of an insertion, it could be just a single insertion or an insertion of a range. It doesn't really matter. Let's just do the copy. One copy and not two copies. So, before I show you how to do that, can you do that? Pause the video, go rework this code. See if you can make it more optimal. And also see if you can write some tests, some timing tests. Use the built-in stopwatch that comes with .NET and time this really expensive implementation, and then optimize it, and then time the result. That's what I'm going to do. This video is probably going to get a little bit long, I'll tell you up front, but if this is interesting to you, keep watching. And pause the video here, go do that, and then come back. Okay, I'll tell you up front, I'm going to do a little bit of hacking, a little bit of bashing around, but I think it'll be useful for you to see my approach to brute forceness. Okay, first of all, it's going to be rough testing just 7 items. I need some real long sequences here. So what I'm going to do is say, hey, give me an int array, a bunch of items. Gets enumerable. This is a built-in class. .range. I want to say 0 to 100,000. We'll get 100,000 items. So range, enumerable.range, produces a sequence from the starting item here, start, and then the number of items. So we'll start at 0, and we'll count up to 100,000. Actually, that'll be 100,000 minus 1. And then I obviously want this to be an array. I could leave it as a non-enumerable. You know what? Let's why not? Why not? We can. You know what? I'm going to say .toArray because I don't want to deal with the underlying headaches of range here. Range actually has some cost to it when we iterate. It's a whole bunch of deep details. Just trust me. I'm going to say, hey, convert that to an array. We get an array. Obviously, I'm hogging up some memory here to get a bunch of items. But there we go. And I'm going to say, hey, my party ages. Why don't we add range a bunch of items? Okay, and let's console write line my party ages.count. Control F5. Hopefully that's 100,000. Looks like it's 100,000. And let's just for each int I in my party ages. Console write line I, but I'm going to get rid of the line part here and just do a plus. And hopefully you'll see it zip past the screen. It's looking like we're getting something that's counting 99999 right here. Looking good. So we now have a list with a bunch of items in there. Okay, and then after we add the range, we're going to say, hey, my party ages, let's insert range. Okay, I'm going to insert a range of items. What I'm going to do is insert my party ages is at index 5. I'm going to insert a bunch of items. Let me see if I can illustrate what I'm doing here. Here is our 100,000 items in an array. I'm not going to draw it all, but here's item 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 100,000 items. Okay, I'm trying to insert another 100,000 items. That means I'm doing it at index 5. Well, index 5, I'm going to guess, is right about here. That means all of these guys are going to have to shuffle. I'm going to have to copy them. That's going to get expensive. It's going to go off the edge of your screen. I'm going to have to copy them all out here. And then we're going to take a bunch of items and copy them in here. So hopefully you're seeing all the overhead we're trying to avoid here. But it should work. And let's console write line my party ages dot count, and hopefully that's 200,000. Now, obviously it goes very fast in front of us. You didn't even notice it pops right up, but it worked. And I want to get on the level of the CPU. If you've seen Men in Black and they talk about Orion's belt, I want to get at the level of Orion's belt here, meaning computer time is a lot faster than our time because computers think so much faster. Well, I want to time this. I want to see how expensive it is in terms of clock ticks, computer ticks, CPU ticks. But before we do that, let's actually see how many resizes we do. Let's just do console write line resizing. Control F5. You can see that there's several resizings here. Many of them are due to the fact that our initial size of the list, we started it out, I believe, at 0 or maybe 10. I can't remember what our default value was. 5. Okay, our initial capacity is 5. And so when I say add range, that's going to cause a lot of resizing. But then let's say inserting here, Control F5. You can see with the inserting only caused one resize because our insert capacity hits the target length the first time. We've seen how to eliminate all these. The way we eliminate all those ones is by stating our initial size. Again, I'll show that to you. I'm just going to say, hey, our initial capacity is 100,000. And now we only get one resize, and that resize is only with the inserting. Hopefully that is review to you. Anyway, I'm taking that out. The thing I'm most concerned about is this insert range. The insert range causes one resize here, and I know with that resize, it resizes, copies all the items, and then it has to shuffle the items and then copy the new items in. I want to get rid of that extra copy. Let's time how long this insert range takes. Stopwatch, timer, it's new, stopwatch. Stopwatch is a built-in class. Timer.start, timer.stop, .stop, and then down here I'm going to say, tell me timer. Timer. Let's look at the elapsed ticks. Technically, this is, or it should be in theory, it's the number of clock tick CPU cycles that the CPU performed. If you look at regular ticks, there's only 1,000 ticks per second, but hopefully you have a CPU that thinks more than 1,000 times a second, or cycles more than 1,000 times a second. And so elapsed ticks actually looks at the built-in clock ticks, but that's also debatable as well. You can go look at the game engine playlist if you're interested in looking at that. I think I did a profiler in there, and I examined it. We see that even elapsed ticks probably doesn't count the actual CPU cycles that your CPU makes, but it definitely counts more than 1,000 a second. In fact, it gets pretty close. Anyway, I digress. I'm going to say elapsed ticks divided by stopwatch dot, there's a static field here, frequency, that's the number of ticks per second. So tell me the number of ticks that happen. Divide that by the number of ticks that the CPU guarantees per second. But if you look at this, I'll say Control KI here and get the IntelliSense up. This is a long. Control KI. This is a long. A long divided by a long gives us a long, which is not a float, and I want floating point here. So I'm going to say, hey, convert that to a float. That'll force this to a float. Force this to a float. Everything will be a float. Tell me the number of seconds it took to do that resize. The number of seconds it took to do the insert range is 0.001. Well, I think we could bump this up. Let's add another 0 here. Control F5. It still runs pretty quickly, but you can see now we're taking 100th of a second. Let's add one more item. It was so dangerous. How much RAM am I using anyway? I'm using 1. Then let's see, that's 100. Let's go over here. That's thousands, millions. So 10 megs, or 10 not megs. That's 10 times the size of an int because we're storing ints. 10 times 4, whatever that turns out to be. Anyway, I got that much room on my laptop. Okay, 0.12. This insert range, it took 0.129. Very good. Okay, that's something I can measure. That's a time I can see. It took 0.1293, whatever that is, of a second to do that insert range of a bunch of items. And that's actually not bad considering the clunkiness of how we wrote this code. But now I want to change this code to where we optimize it and don't do the double copy. There's a copy here and there's a copy here. Let's just do one copy. I want to change this code so we do just the one copy. But before we do that, let me just throw this number to the side. I'm going to right click in here, click mark, highlight this, hit enter, open Notepad. I'll paste that right there. That is our clunky time. Let's go rework our code, see if we can make it a little bit faster. The problem with this, though, is now we can't rely on ensure capacity. Ensure capacity is a nice helper function that makes sure we have enough room for whatever we're trying to add or insert. Now I have to ditch ensure capacity because I don't like ensure capacity's copy. So I'm trading some maintainability here for some optimization. And generally I don't optimize prematurely as I'm doing here, but if I was working for Microsoft and I was writing a list, and I can guarantee you that the built-in list for Microsoft is used everywhere and so all over the world, I'd probably want to make this as optimal as possible. So there's two approaches here. Let me just show you. Let's say our underlying sequence, let's say we had, I don't know, 31, 8, 24, and we're trying to, I'll extend this a little bit. Let's say our capacity is 1, 2, 3, 4, 5, 6, 7. Our count is 3. let's say we're trying to insert 2 more items. Let's just do 99 and 100. All right, I'll make that our range that we're trying to insert. We're trying to insert it right here. Well, in that case, we don't have to resize our underlying array because our underlying array's capacity is larger than the number of items that we already have, our count, plus the new items count. All I have to do is shuffle. The 24 has to come down here, the 8 has to come here, and then the 100 will go here. And the 99 will go here. I'm being lazy and not erasing here. But anyway, you can see that if our underlying array is large enough to store everything, then no optimization necessary. And that ensure capacity call that we had here, we Control Z, bring that back. That ensure capacity call that we had there would do nothing as well. So not a big deal, but I'll take that out again. And we'll just say, hey, you know what? If the number of items we have plus the number of items we're trying to stick inside of our array is greater than our capacity, then we're going to have to do some special optimization code. Else, just do the shuffle. Let me clear this off, actually. Let's just do the shuffle. Sorry, let's see, what time is it? It's 5:27 a.m. I'm a little zonked out right now. Just do the shuffle. All we got to do is the shuffle. Otherwise, we need to do the shuffle, but we want to avoid the double copy. We need to allocate a new array, that sort of thing. Notice I kept the for each out here, though. Copying the new items from new items into our array is the same, no matter if we're shuffling or not. Just right here, I'm trying to avoid the double copy. We know inside of these two curlies here, we need some room. We need to reallocate our underlying array. So I'll say T array new items gets new T array count plus new items count. And of course, new items is a terrible word. How about new underlying array? The reason why I was getting rid squigglies is because we already had a new items, and you can see I'm terrible at these variable names. New underlying array. Let me draw a scenario back up again. Here is our current underlying array. We'll just say we have a 32, an 88, a 94. Let's add one more. We'll say 52 out here. We're trying to insert, I can't remember what numbers we were trying to insert, 8 and 21. So we'll say this is new items. New items. And this is our items. This is our underlying array right here. And then obviously our capacity plus our count. Our capacity is 4, our count is 4. We're trying to add new items count as well. So 6. Well, 4 plus 2 is 6. 6 is greater than our capacity of 4. So we will allocate a new underlying array. That's obviously not going to be long enough because that'll go off the edge of your screen. So new underlying array. We could double its length or something like that. But for now, we'll just go to the exact size that we need. And in this case, we're going to have to do 3 copies. Let's see, if we're inserting this 8 into there, then we're going to copy these values over to here. So we'll have 32, 88, then the 94 and the 52. There's another copy. That needs to go here. So 94, 52. And then these items actually go right here, and that's handled by this for each down here. So this copy is done. This copy in the middle, that's a done, happy copy. But we need to do this original copy where we take the items before the insertion. We need to put them there. So array.copy. We want to copy from items into our new underlying array, and the number of items we want to copy is the index. Okay, in this case, index will be 2 because we're inserting at index 2. This is index 2, 0, 1, 2, and the number of items we want to copy is the index. So 0, 1, or 1 and 2, that's the number of items we want to copy. That's what we're copying right there. So there we go. We just did that copy. Good job. We know that this copy is done. The last thing we need to do, and this is the optimization, is we're directly copying the shuffled items into their proper area instead of just copying the items we're shuffling into a new area and then reshuffling them. We're copying them to their destination. So let's go down here and say array.copy, again from items into our new underlying array. We're going to have to use some overloads here. The source index will be the index that they're copying from. In this case, index will be 2, and that's where we want to start. 0, 1, 2. Right now, items is this array, so we want to start at index 2. Then where do we want to put the items? Well, we want to put it at index, which is 2 here. This is 2. 0, 1, 2, 3, 4, 5. We want to go to index plus the number of items in our new items array, which is right here, new items count. So let me put that in there. It's going to be index plus new items count. Wow, this is getting really messy. I'm sorry. I'll hit enter there. Just move it to a new line. And then how many items do we want to copy? Well, we want to copy the count of items we currently have minus the index. Okay, the index will be 2. Our count will be 4. Right now our count's 4. We want to take off the index of 2. So 4 minus 2 will be 2 in this case. But anyway, the count of items minus the index that we're inserting. There's our shuffle and our copy. That's our optimization all in one. And then we need to ditch the old array items. Is currently referencing this old array. We want it to reference our new underlying array. So new underlying array. And I think we're good. Let me get all that off the screen. And I think we're good. Let's Control F5 that. Hopefully it runs faster than our previous one, and it looks like it didn't. All that work and actually ran slower. Okay, we didn't gain much here. You can see here's our old time. We do that shuffle, and where's the expense in this? Where's the expense in this? Give me 1 second. Let me see what I did wrong. Okay, so I did some experimenting offline, and obviously these times are, sometimes I get better, sometimes I get worse, but all that work, all that optimization, and we didn't really gain anything from it. And so that's another reason why you don't want to do premature optimization. I've said this in several videos, but here I am prematurely assuming that the shuffle or the copy to a new array and the shuffle is costing us a lot of time when it actually isn't costing us as much time as some other parts of the code. And let me show you what I've found here. I'll Control F5 that. You can see that our new time with the ignoring the copy and just doing the shuffle while we copy, our new time's not that much better, and sometimes it's even worse than our old time. What I found is the real expense sits right here. Remember, count brute force count does a brute force iteration through everything in the new items to get that count. And then, oh, look at this. We're iterating all those items again. So here's one full iteration. Here's another iteration. Also the addition of the copy. But the bad thing is we're just iterating or enumerating through all of the new items twice. Let's see if we can avoid that. And here's one of the most fundamental, basic, famous, common trade-offs you'll ever make in your computer science career. The trade-off is memory for speed. To iterate through a sequence, it doesn't generally take up that much more memory. Maybe a little bit of memory for the enumerators and that sort of thing, but it doesn't take up that much memory. However, in this case, I have to iterate the items twice, and I don't want to iterate the items twice. I need to know the count beforehand, and then I need to do the copy after. But what if let's do a little trade-off here. I'm going to say, you know what? T-array, new items as array gets new items dot to array. Okay, this will be our initial iteration through the new items. I can say dot length on new items as array, so I get the count. I also get one iteration here, and then instead of doing that clunky for each down here, I can say array dot copy. The source array is new items as array because I now have that array. I've taken up some memory for some speed. I'm trading off RAM for speed. This obviously takes a lot of memory to do a copy of that sequence that underlies our new items, but I'm trading memory for speed here. New items is array. The source index will be 0. The destination array is items. The destination index is index. And then the number of items I want to do is new items as array dot length. Okay, because this array stores its length. I'm going to get rid of new items count because I no longer want to do this iteration again. You can see that gives us a lot of red squigglies, but now I can say new items as array dot length. That's just the new items count. And put that there, put that there, put that there, put that there. Build. Build succeeded. Now that we have this copy, we no longer need to do this for each. That for each is no longer necessary. Control F5, run that, and hey, look at that new time. It's 0.04 seconds. Our old time is 0.12 seconds. So we're almost about a third faster by trading this memory for speed. We got 4 times faster. So not bad. Not bad. It does make you wonder, though, if we just went back to calling ensure capacity. And yeah, sure, ensure capacity is going to do a little bit of copying, a little bit of unnecessary work. Actually, probably a lot of unnecessary work. But you notice this array copy function. Once you have the array copy function is actually pretty fast. So it makes you think, do we really need all this headache? Could we just go back to calling ensure capacity and then just doing the shuffle afterwards? How much more expensive would that be? I'll leave that as an exercise for you to rework this code back to doing that. One thing I also want to point out is we haven't been testing any of this. We don't even know if our code actually works. I know I'm slamming 100,000, whatever, 10 million numbers around, and we haven't really tested this written test to make sure that this code is actually doing what I think it's doing. We should write unit tests to test that, but the video is already way longer than I've ever done any other video. But I think maybe just a basic visual test, just because I think it's important. Why not? 1, 2, 5, 6, and then my party ages dot insert range at index 2. I want a new array. I'm going to put a 3 and a 4 in there. And then for each, int I and my party ages, console write line I, and I'll just put a return here to ignore everything else we're doing. But if our code works correctly, we should see 1, 2, 3, 4, 5, 6. And we see 1, 2, 3, 4, 5, 6. So very good. Visual test. I told you I'd leave this as an exercise for you, but I'm going to actually just do it. Why not? We'll do ensure capacity, count, plus new items as array.length. We'll go back to the old school way of doing it. Control L. Let's just make sure it still is 1, 2, 3, 4, 5. So yes, that code works as I think it would work. But then let's go back to doing the hardcore tests here. We do 10 million items. Control F5. Of course, there's build errors because my party ages. Let's bring that back into scope. Get rid of this. Get rid of this. Control F5. And there we go, 0.05892. Before we had like 0.04. So to do the copy and then the shuffle, the little less efficient technique, that still takes more time, but it's not nearly as expensive as I thought it would be. So learn from me. That's premature optimization. When you optimize, generally you want to find the code that's called the most, and you want to find the code that takes the longest. The only way to do that is by using a profiler to find code that hits both of those scenarios. But in this case, I was duplicating the built-in list. So I just assumed this code would be called frequently, which I'm sure it would be if I was working for Microsoft and distributing their list. I would almost guess list is one of the most used data types inside of the .NET framework.